Hi, welcome back. So we are in Chapter 6, Prediction by RCC, to discuss the outline prediction by classification, in particular deep learning. We have established so far the mechanism or the idea of the framework of a neural network, and we have seen a practical example actually by building up our own simple neural network, but the principle is in there. You can take that concept and make it as complex as you like. Depends on the dimension of the problem and etc. Now, what we want to work on, actually taking that neural network and build up a new framework, but in principle, the neural network still stand behind. Convolutional neural network, which is in principle actually aspire to make the computer able to emulate a human vision, so to speak. So let's get back in principle and take a real application of CNN, and one of the best is to recognize an image, for example, if it's given to a computer, and then how can the computer classify an object in that image. If we are talking, for example, about face recognition, one of the earlier problems, so far we have learned some of the algorithm and we drop out the neural network. For example, we could use the subperfect machine, maybe logistic regression, though, naive Bayes. Maybe they were able actually to recognize, face recognition, because it's a classification at the end of the day. But I think the complexity of the problem have evolved when we are saying, well, I'm giving you an image, but inside the image, there are different objects, basically. And how can I ask the computer to recognize these objects? In the recent years, magnificent work has been done on that, in particular in the field of something called computer vision, and I think there was a huge improvement over the years. Now, what we're going to do actually, let's just start with a flow chart of this framework. Now, we're going to work on only one image. Well, every pixel represents the presentation of that image on the screen. Now, from mathematical perspective, this set of pixels, it's just a matrix, and this is what we know. So if I would have to read this matrix, we know very well now, reading the number of rows multiplied by the number of columns, that give you the total actually number of pixels that represent that picture. Imagine if I would have to take this particular row. Basically, this 0 row would have number of feature or the column space in this case, right? So we have like n of these guys. And now, if you would have a picture and we take a certain attribute, let's say color. One is color, one is no color. And basically, when we say no color, we always indicate a grayscale image. And when we say color, we are talking about the red and the green and the blue. It means when I get back to my image in here, I would have like to have this R by C, the same number of rows by column, but this time there are 3 of these matrices. So this is my red, this is my green, and this is my blue. This is a very important way of reading an image. Just we're talking about a single particular image. All these principles are important, and you have really to understand them in order then to move forward. Let's just start talking about the CNN. What is it in principle? Well, the CNN says, let's take non-color image. Just a grayscale. When we talk about grayscale, I'm talking only about R by C. Every pixel here represented either by 0 or 1, or maybe even a scale of 255 numbers. It doesn't matter. And so we take like 16 by 16. And I want to make some operation in this image. Design a square filter, 2 by 2, maybe filter 3 by 3. Let's take the simple 2 by 2 filter. I will call this value for now alpha 1, alpha 2, alpha 3, and alpha 4. And I'm going to pass it over this matrix here. Let's make dot product. Take x1, which is the first entry from here, multiply by this alpha 1 plus alpha 2 x2 plus alpha 3 x3 plus alpha 4 x4. And then you will get a number here. And we're going to take this one and slide it the right hand side of the image by, for example, say 1 slide. And the same exact operation, you repeat it again. Now the alphas are the same, but what has changed now? We're going to start from x2. So it's going to be again alpha 1, but now x2 plus alpha 2, now x3 plus alpha 3, now x4 plus alpha 4, now x5. And then we get a new value here. Let's call it 2. And slide one more time. Let's actually, for simplicity, I should design this back to 6 by 5. We say we're going to stop somewhere here. Alpha 1 still is alpha 1, but tell me what x here we're going to stop at in horizontal wise. Every time I move, I have to check the criteria. What I want to make sure that the filter is moving in a horizontal wise, it doesn't exceed a certain number. And what's that number correspond to? Maybe correspond to the number of the rows, which is in this case 5. But what is the number we're going to compare that to? Well, it's obvious that the size of filter. We know the size of the filter is 2 by 2. It means the length is 2. So basically we could say, well, if we fix a arbitrary number, we call it the C number. Now C is equal to 2 because 2 is the length of that. I ask, is 2 less than 5? It says yes, then do this operation. So we're done here. Increase this to 1, so this becomes 3. And then ask again, is 3 less than 5? Then take the step and do the second one. So in this case, what we're going to have V1, V2, V3, and V4. Then we're going to take this filter and move one step down. So now we are starting from the 1 row. And the same exact operation have to happen again. It seems like there is an inner condition and there is an outer condition. The outer condition is checking row-wise, and the inner condition is checking column-wise. And then we can get finally the new matrix. Obviously, one important thing you can see from here, that the new matrix is absolutely going to be smaller than this. And the question is there a way that before we do this manually, can we have like a certain function or an equation can tell us exactly what is the number? Well, it turns out there is, which I'm going to share with you right now. If we take the dimension, either row or column, as you like, doesn't really matter, and we subtract that from length of the filter minus 1, then you will get actually the total outcome. If we take the dimension of the row, that is 6 minus, and the filter length is 2 minus 1, that will lead me to the result of 5. And if we take the column correspondence, that will lead you to the value of 4. With a new matrix, the dimension of it is 5 by 4. So we have transferred the 6 by 5 into 5 by 4. This is the essential idea of the framework, by the way. It's nothing special. Now the discussion starts. Why are we doing this, and what is the benefit of doing that? Well, it says as if to transform X feature into a radial basis function or maybe a polynomial. I mean, the inspiring idea is something similar to that. It turns out if you do this, you will get something out of these 4 pixels and then something else out of these 4 pixels. Depends on these alphas actually. Alphas can make a sense of detecting, if so to speak, something out of this picture. Now, if we modify this a little bit better by adding to every one of these guys here some bias, we are sticking into the same exact idea. How many alphas actually we need for this? It is obvious that each one of these guys will need alpha. This is one equation which corresponds to that. This is another equation, and this is another equation. So each one of them, 5 by 4, which is 20 of these alpha knots. And then we will have only a matrix of 2 by 2, actually normal alphas. What we expect from all this operation is to predict something, to classify something. And then if our classification is wrong, we should get back and change these alpha. The principle, again, is the same. I think then the idea of the framework evolved even better by saying, well, how about we add buffer around this image? In this case, we're putting 0. It will cause like a black border around the original image. Let's start from here. So we are just dedicating the investigation onto this particular pixel. So here we have just learned a new mechanism. Well, sustain the same framework, nothing has changed. We add the buffer. We need also to modify this equation. Our equation should look like this. Well, this is the 6th dimension minus, well, we did not do any buffering here, so it's going to be 0. 2 multiply 0, 0. Minus the filter, it is 2. The length of the filter, and then we have 1 straight, it will add 1, that is 5, which correspond exactly to the idea here. And same thing, you can do it to the 2nd dimension. But now let's also work on the filter itself. Well, if I am able to apply 1 filter to this image, can I apply another filter? And the answer is yes, you do. So imagine I have 1 filter here, and the operation of this filter will lead you to a certain outcome. Let's apply 2 of these filters. And here we will have another set of alphas. 1 alpha is here. Now we have different alphas, which is going to be exactly the same like the previous one, but both together to form such a volume. For example, if this is the outcome of V1 from the filter 1 and this is V2 from the filter 2, dimensionality is exactly identical. When I did this operation by joining both of them, I will have actually n by m multiplied by 2. Well, this 2 could be actually as many filters as you like. The idea of filtering principle, these alphas actually, they are doing something. Each one of them can be responsible for something. For example, I could design a filter that is interested to find a kind of a vertical lines, maybe another kind of horizontal lines, okay, another kind of diagonal lines. So each one of these guys could represent one filter. If I pass this to this matrix, it will actually dismiss everything else and just only look for these particular lines. And same thing here. And the outcome of this, I will have 4 different of these guys here. And if I join them all together, you will have this dual kind of a matrix at the end. Now, the last things to talk about, the colorful one. The colorful one, as we say, we have RGB. But the only difference here now, this 5 by 5 matrix, it's going to be now 3 of them. So red channel, green channel, blue channel. And that means, for example, I would have here now, if I want to present this number, I'm unable to do just only 5 by 5, but I have to present a number of channels. In this case, we have 3 channels. Well, the exact same principle, if I take this to a convolutional processes we've been talking about, again, I can apply that. So I have like 4 by 4, it's the outcome. But here you have to be quite a bit careful. It is going to be the outcome of one of these guys, right? So as we said, so I would have 4 by 4 again multiplied by 3. And if I would have only the case of one filter, this is very important to recognize, because this would be the outcome of only using or applying one filter. But how about if I apply 2 filters? Well, I would have 2 of these guys. This is where the complexity of this framework it become quite a bit intimidating to many different people, because they thought this is mathematics. It isn't. It's actually a framework design trying to visualize the idea of that. I can do this as many as I like. Maybe I can create again a new set of alphas in next step, and I apply it again on this new outcome. But they say, well, how about that? If we do something called pooling. This time I'm going to create a mask. This has no alphas at all, 2 by 2. And again, I slide over here and look which is the largest number among these 4. So you could see the outcome of this max pooling. You will end up actually with something looks like this. So this is a huge reduction in the size of this convolutional outcome into this new pooling. Another alternative technique, maybe instead of pulling out the maximum number out of these 4, maybe you could pull something called the average value of these 4. So you could also rely on that, but the idea is in there. And once you have this a new outcome after the max pooling things, again, you can put it inside convolutional process like we did it by designing a new alphas and etc. And one more last thing I would like to tell you, that the outcome of each one of these convolutional steps, I mean, using our equations, the alpha 1, 2, all the ways, maybe you can do something with it. How about if you apply the Riemann function into it, or sigmoid or whatever? So here this same exact thing is repeating again and again and again. So what is the outcome of all of this with this improvement on the framework by max pooling or adding average, the Riemann, etc.? I'm going to show you the final things and why is that looks like intuitively good. If you take this and you flatten this into one single input, so this now a single input, I can take this one into a newer network. The same framework we've been working about. And then finally, you can predict, for example, the probability of 3 values. So I think this framework here down should be very much familiar. What has changed is this input space, the transformation of this input space, which has come actually originally from this image. Now let's go ahead actually and apply just maybe the first step of this guy here, and let's see what that looked like. I would like to start first of all by importing this data set from sklearn. So if you print the shape, the result looks like this. And what does that mean exactly in particular? Well, it is obvious that we know this is my number of rows and these are my number of columns. And then what is this? This represents how many images are in there. So you could imagine 1, 2, 3 all the way to 62, and then we have 1, 2, 3 all the way to 46. 47. Now this represents an image, but still this can be considered as a scaled an image. It means a non-colored one. How many of these we have images in here? We have 1348. So image number 0, array of numbers, which we know it should be like 64 by 52, right? Now if you go for 0, that will be an array of 52 numbers. Now what we want to do here, we want to create padding around this image and then do the filtering on that. Now if I want to pad this image, there's small things that we have actually to understand. The image, it isn't in a kind of a squaring value. So when you actually want to fix the filter on it, you will always have an odd number at the end. So you want to make sure the filter, it match the motion of stride, right? So I wanted to add padding here with the number of rows and columns, but make sure that is going to fit okay with a filter 4x4. Print that out. You could see the original size was this. Now it becomes 64 and 47 become 52. Here we go. If you like also to graph, you could see the difference after the padding, which represent with this border of black color. So let's now work on the filter. Now I have just initialized two different filters, one of them completely random values of filters, and the other one much more planted one with, single numbers, positive and negative, and some zeros are out there. By the way, when speaking about filter, if you check the text box, there are many different, this the Gaussian filter, the Go filter, and each one of them have a different job to do. Some of them detecting edges, some of them detecting angles, and etc. So I just created two different filters for illustration purpose, and we can see them in down here. Then let's graph actually the image, what that looks like. So this is the original shape, and this is after we transformed to become 61 by 40. You could see quite clear. And which filter we are using here? By filter 1. If you multiply by filter 2, you see it's completely different things had happened. Maybe it's much more sharper to look. These are the random numbers, right? So you could see each filter is going to show you different characteristic of the image. Let me show you something quite a bit interesting. Maybe we could just look at one filter operation. We are at the matrix size, the first side of the matrix. Now we multiply by the filter. Watch carefully the outcome, which is going to be exactly like that. We are touching this side of the image. That's why the filter was doing here. And here is another side of the image, and you could see the filter operation in there. What had happened actually, it just ranked a different presentation and another. That was all concerning the framework of CNN. Perhaps next maybe we can discuss another framework. That's exactly what we're going to do next. I will see you then.